Okay, welcome everybody. This is section 7.5, and we're going to use integration to calculate work. So work done by a constant force, that's your basic physics class when you take a basic physics class. Has everybody, or are you taking physics 1 now? Is anybody taking physics 1 right now?
Yeah, I'm doing university physics right now.
Yeah.
I took it last night.
Yeah, normally you take physics 1 when you take calculus 2, and then physics 2 when you take calculus 3. That's how I remember it. Okay, work done by a constant force. I mean, the formula is just force times distance. And a lot of times when we're using force, we're talking about a weight of an object. And this, once again, this is basically the formula, the very basic formula that we're going to be using over and over this section. Trying to get to the next page. There we go. So once again, work equals force times distance if you have a 50-pound object. And lifting a 50-pound object 4 feet. $200. What is the units for work right here if we're using pounds and feet?
Foot pounds?
Yeah, it's foot pounds. So we use foot pounds.
I have a question, sir.
Yeah.
You wouldn't have to convert that weight into like newtons or like a unit of force. It's fine with being.
No, foot pounds is a unit of work. No, you can't. I think the homework might go to newtons also. Newton, and I think that the actual slide will tell us newtons is the amount of work on 1 kilogram over 1 meter. I think it's on a slide here. Let me show. Let's see if we can see this slide. Yeah, right here. So yes, if we're using the metric system, we are talking about newtons. The force required to produce an acceleration of 1 meter per second on a mass of 1 kilogram. Yeah. So that's when we're going to be using newtons. So yes, I when you're using physics, you're always staying in the metric system and all, but we're using it also. A work foot pounds is a unit of work also. Oh, and also it talks about joules down here also. Newton meters or joules. Now work done by a variable force. So we're still using, if you look, the integration, force times the change of x, which is the distance, the force times the distance. So we're still using that. And then we're going to get to the actual formulas. So we're going to look at the different, so I mean, this is the key, this force part is the key for the integration. And you're going to see what the next slides are going to show you is that force part can change a lot depending on the situation. The actual force can change a lot. And we'll see. Hooke's law deals with the spring, and these are our usual problems in physics and in this class. where you're compressing a spring or you're stretching a spring. And the formula is force equals K times D, where K is the constant that deals with that particular spring. So that is a constant. And it changes depending on the spring you're using and the length of the spring, the material you're using for the spring, proportional to the distance, and where it is. Where does it say anything about K? It should, oh, where the constant of proportionality K, it's a constant. And it just depends on, like I said, the material that the spring is made out of, how thick it is and all that. There's a constant. And normally we're finding that K. Then there's also another force, Newton's law of gravitation. Two particles and the distance between them, the masses of the two particles. And I don't remember seeing this in the homework, but they brought it up also. I just don't remember seeing this formula in the homework. But and they're only showing 3 in these slides, and I'm not too worried about discussing them. I want to do the actual ones that we're going to have in the homework and on the tests. And then there's Coulomb's law, where it deals with electricity, the charges between two particles, electrostatic units. And once again, there's the K, and there's the charges of those. And this is, I don't know if anybody's going to become an electrical engineer, but you'll deal more with electricity and stuff doing this formula later on. All right, so let's go to the compressing of the spring. Once again, our integration, our main formula looks like this. And we also have force equals K times D, the constant times the distance. So these are the two things we got from above. So it says a force of 750. If we look at that, I'm going to write 750 for force. Compresses the spring 3 inches. This is the distance the spring gets compressed or stretched. And we have to find that see this paragraph doesn't give us the constant for the spring, the K for the spring. So we're finding that first here. 3 inches from a natural length of 15 inches. So we know the spring is normally 15 inches. And there's a force of 750. We need to find the K. Just take the 3 over to the other side. So K is 250. So since force is K times D, we have 250 times the distance, and the distance is going to be X, and then dx. Okay, so if you look at this first part, and for all these spring questions, there's usually a first part, and in that first part, we're usually trying to find the K somehow. So I just want to make sure we understand this. We have a question in the homework that's similar to this, but we're finding the K a little bit different. They give us the work. Oh, by the way, this is the formula for work. Okay, now, so if you look at what I just circled, that part of the question, we're done with that part of the question. We don't need any of that information anymore, really. I mean, Now we're going to try to answer the question. It says, find the work done in compressing the spring an additional 3 inches. So right now, our spring, here's 15-inch spring. Our spring is compressed 12 inches. You see, compressed 3 inches. There's 3 here. So we're at compressing 3 inches. It says, find the work to compress it an additional 3 inches. So we want to squeeze this spring an additional 3 inches. So we're going, and this is how far the spring is compressed. It's compressed 3, and then it's going to get compressed to 6 inches total, because 3 more inches. So that's important to know. The A and the B, where we're integrating, is where is the spring compressed? So this is it. This is the problem. I mean, we integrate that and we're done. It's a very simple problem. Let's take a look at it. I'm going to erase the stuff on the right-hand side, but that's it. Let's erase this stuff. And when we integrate 250x, we get 250x squared over 2. And we are integrating from 3 to 6. We could reduce that, 125x squared. 250 divided by 2. So we put 6 in there first. 125 times 6 squared, 36. Is that right? Did I don't think I hit 125 times 6 squared. 4,500 minus 125 times 3 squared. So we get 337.5. And the units, I know a lot of teachers like the units. I'm not too worried about the units, but I do want to write them down. I don't think there's going to be the same answer with different units. We're dealing here with inches and pounds. So this is, instead of foot pounds, we're using inch pounds, which is a unit. Units of work also, foot pounds or inch pounds. I mean, the spring problem is not too bad. There's one in the homework that it takes a little twist on finding the K, and we'll get to that. But that's, I mean, this is a very typical question on the test, and I think I showed a spring question on that show your work. You saw there's not a lot of work here to show. This is it. All right, so we did 1. Oh, they do. They go and explain it. I'm glad I didn't hit next. And you can see them going through the whole process. First, you're going to find K, and then we ended up with our F as being 250x because our K equals 250. And we're integrating from 3 to 6. We start with the spring is compressed 3 inches, and we end where the spring is compressed 6 inches, 3 inches more. And we do all that, and we get this. Let's try this next one. 20 foot, same as this number 5. You'd be surprised. I matched this up with a problem that's in the in the homework. There's one in the homework that's similar to this, but it really is different. It's kind of cool. I think we'll see. A 20-foot chain weighing 5 pounds per foot is raised 20 a 20-foot chain weighing 5 pounds per foot is raised 20 feet. What is the work? Okay. Oh, there's a picture in the book about this. So there's more. I think when I originally did this PowerPoint, I left out a lot of words. So there is a 20-foot chain. It's on the ground. So let me be specific. It says it's coiled up on the ground. And then if you look in the book, there's a bulldozer or something like that that's going to pick up the chain, and it's going to start, bringing the chain up piece by, the chain is going to start being brought up. And they want to know the work required to bring that chain up. Okay. And they're using, since the chain is going up, they're going to use Y instead of X. They want to know this is the distance that's going to be 20 feet. The chain is going to be 20 feet up. So once again, work equals force times distance. Work equals integrating force times the dx distance. So just like that first problem we had on weight, this chain is 5 pounds per foot. And it's curved. So you see, when it first comes up, it might be 1 foot. Then as they bring it higher, it might be 2 foot. So this chain is being brought up. So it's going to be 5 pounds for every foot that it goes up. The force is 5 pounds for every foot that this chain comes up. If they only bring up 1 foot, then it's only doing that 5 pounds of work there. But when they bring it up another foot, now they have 5 pounds times 2 feet, 5 pounds times 3 feet, and so on and so on. So this is the actual formula here. Instead of dx, we're using y and dy because I'm just following the book. You could use x and it doesn't matter. But since they're showing that it's going up, we're using the y direction going up, so we're fine there. And the chain starts on the ground at 0 feet, and we're going to take it all the way up to 20 feet. The chain is 20 feet long, so the whole thing is going to be raised up right up to 20 feet. And this right here, that's it. This is the formula. This is the problem. And it's, once again, this is a very easy integration. Integrate. We're going to integrate from 0 to 20. When we put 20 in there, we get 20 squared is 400, right? 20 squared, 400 times 5 is 10,000.
At 2,000?
Yeah, 2,000 times 5 Why did I get something else when I did this earlier? Oh, we have to divide it by 2. Yeah, 5, you get 2,000, then divided by 2, you get 1,000. And once again, we're raising it in feet and pounds, foot pounds. So that's, I mean, that's not bad. So far, the first 2 seem really easy. And these are the 2 typical questions we have on the test, the chain one and the spring one. So I would concentrate on those, but I did want to show other possibilities. This one here, this is a tough one, but I do want to show it. I'm going to go through it really quick and just show you. So you have this spherical tank. This is a tank and it's filled with oil. It's a huge spherical tank. What is it? 16 feet tall. Yeah. And it has a radius. So it has a diameter of 16 feet. It has a radius of 8 feet. It's a huge spherical tank and it's filled with oil. It says it's half full of oil. So this tank is half full of oil. Find the work required to pump the oil out. So we're right now, this Y level is 8, right? It's from 0 to 8 because it's half full. So we know it's starting off at 8. And we're going to pump the liquid out of here. So it's going to get the liquid, the oil is going to get lower and lower and lower eventually till we get down to 0. That's the goal. We're pumping the liquid out of here. And it says, find the work required to pump the oil out. Also, so I also want to show you, they're talking about using discs. So we're going to we want to use a disc. So this is a circle. And we want to find the area of the circle, but it's a disc. So it's the area of a circle, and then multiply it by the width of the disc that we're measuring a whole bunch of discs, you know. So it's circle with some depth to it, with a width. So the area of a circle is pi r squared. And then we want to measure the height, you know, the pi r squared height for each ring. You know, this has a thickness to it. So that's what we're looking for. I just want to explain what we're doing in this problem. And I think they talk about this also in here. Spherical tank, radius 8, is half full of oil, weighs 50 pounds per cubic foot. So that's important, 50 pounds per cubic foot, because that's a measurement of volume. And if we do pi r squared, the circle, the area of a circle, that's 2-dimension, that's not volume, but we have to add the thickness, the height of the disc, or you can even say the Y, the length of the disc. And then now we have volume. So we needed to know that. Oh, and they're saying the thickness is change of Y and the radius is X. Okay. So the thickness will be the change of Y and the radius is X. Pi, so our formula will be pi r squared, and then height. So it says the radius is X. So it's going to be pi x squared, and then H is going to be the change of Y. So we're going to, so this is really important. We're going to take the integration with respect to Y here. And this is really important. I mean, we haven't even started yet, but I want to show you that means we have to get rid of this X because we're going to integrate it with respect to Y. So somehow this X has to change. into a y somehow. I mean, that's what, when we integrate with respect to y, we need y's. So, I mean, I'm just talking and I'm thinking about how we're going to approach this problem. And that's how we approach it. Okay. So we are going to do, once again, work equals integrating force times distance. Except I'm just going to write down the formula that I wrote down. Let me put it right here. Yeah, I guess I can put it right here. So the force is the weight. And if we go back, it was, remember, see how easily I forget things. Right here, the oil weighs 50 pounds per cubic foot. The oil weighs 50 pounds per cubic foot. So we're going to start off with, we're going to multiply, or we're integrating with 50 pounds per cubic foot here, times the area, right? 50 cubic foot times each disc, and the discs were pi r squared, but we changed it to x squared because r is x in the picture. And we are integrating this with respect to y. All right, so let's see how this, so what we're doing here. So I mentioned we have to change that x square. And if you know the formula, so of a circle, does anybody remember what the formula that we learned in algebra for a circle is? Anybody know? How do you write a formula for a circle? If you were going to draw a circle, what's the x and y's? How do you write that? Right, x squared plus y squared equals r squared. Does anybody remember that? Yes. This is the formula for a circle.
I mean, I remember that, but not as the formula for a circle.
Yeah. You know, when you're graphing a circle, x squared plus y squared equals r squared. So I want to go back. Because, I mean, I'm doing all of this because I need to get rid of this. I like that I have an x squared here. I like that a lot. But I want to see what my y is. So I'm coming back. If I'm coming back here, and the y was, the whole thing is 16 feet. And then as you're leaving oil, it's minus, 1 foot, minus 1 foot, minus 1 foot. That's the distance of y. But we're starting down here. This is our starting point. So our formula it's kind of, well, here's our center. Where's our center? It's kind of hard to see right here. Yes, this is our center, and they're showing that this is -8. So x is right here, but this is -8. So I'm going back. And we have to use one. Oh, yeah. Sorry, we have to change, the x squared is going to stay the same. but our y is not y, it's y minus 8. And we know our radius of that sphere is 8. Since it was, if you looked at the picture, that the actual formula for the circle there, it's the y was 8 over. So this is the formula. I'm going to rewrite it: x squared plus y minus 8 squared equals 64. I'm going to take this to the other side. 64 minus y minus 8 squared. And if you notice, this is what x equals. So I'm coming over here, 50 times pi and x squared changes to this 64 minus y minus 8 squared. Yeah, that's it. And we are integrating from 0 to 8. It's only half full. And I think that's pretty much no, that's not it. So that was a force. We haven't done the actual. So I mean, we're there. This is all of this. There's one more part we have to do. I forgot that. I mean, we're still doing dy, but we still have to do this change right here. And in reality, it's a change in y, and the change in y is I'm running out of room. I'm sorry. 16 minus y. The tank was full at 16, and there's where we're subtracting the y to get the tank lower. That's the distance lower. So that you know, it's force times distance. And this is the distance the oil is going down until it gets to 0. The distance goes down until it gets to 0.
So if we were using a tank that was 20 feet, it would be 20 minus y, right?
Yes.
Even
Exactly.
if we were doing half of that one, it would be at 0 to 10, but it would be 6 to 20 minus y at the end.
Yes, exactly. Yes. And well, and I mean, these just happen to be 8 and 16. This is just the location on our grid. I mean, if you go back to looking at circles, it tells, you know, a circle right here is x squared plus y squared equals r squared. But if we move the circle over, then x, you know, the x, you know, if it moved over to like -5 here, then there would be a plus 5 squared plus y squared equals r squared. You see, this is the position. If you go back and look at this is the position of the circle when we're looking at a grid and that they're showing us. Now, yeah, I don't want to get those two confused with each other. All right, so I'm going to try. I'm going to try to go to the next. Is there another page here? Did I leave myself an extra page? Let's see. Right. Yeah, there we are. We're at this point. So once again, this is the force. This is the distance from the top to the bottom. And you see, if the circle was down here on the x-axis, then you wouldn't have that in the previous that the shifting of the circle. It would, if it was right on the axis here, it's actually up 8. All right. Anyway, we're at this spot, and now we just have a lot of algebra to do. Unfortunately, we're going to multiply these two together. 16y times 16 is what, 256 y squared. 16y times a negative y is a negative 16y squared. Multiply these two together, I get a negative 16y squared, and multiply these two together, negative times a negative is a positive. These two combined, that doesn't seem right. Something doesn't seem right.
Well, where we stopped in the work I have, where we're doing integration.
Yeah, we're not doing integration yet. So, I mean, we're trying to get it all simplified before we do the integration. Wait, 16y times, oh, that's not a 16. Okay, I'm gonna just give me a second. I have to multiply these two, but this thing is disturbing me. There we go. 16y times 16 is 256y, not y squared. That's where I said it was y squared. Now, when I multiply these two, I get negative 16y squared. If I multiply these two, I get negative 16y squared. And if I multiply these two, I get a positive y to the third. These two combine, and I'm gonna put the y to the third first. And then this is minus 32y squared. And then the 256y. So, and there's that, and we're going to go to the integration, and this 50 pi I'm going to put out in front of it. So this is what it looks like that I'm going to integrate. And don't forget, we're integrating from 0 to 8 because only half of the tank is filled. So this is the integration we're going to do. And I'm just wondering if it's on the next page or if I have a blank so I can go through that. Is that the same thing I wrote down? Yes, it's just not in the same order. Yeah. So that's the same thing I wrote down. Now we can integrate where, I mean, put the 50 in front and integrate this 256y squared over 2 minus 32y to the third over 3 plus y4 over 4. And we have the 50 pi in front of it. And then we put 8 in there. And you go through that whole mess. Oh, Lord. All right, let me do it. I'll actually do it. 256 times 64, 8 squared, divided by 2. (32) times 8 to the third power divided by 3. Oh, it becomes a decimal. Let me keep the decimal there. Anyway, when you put my calculator won't even do it. Anyway, if you do all this together, I'm just going to put the answer down. I think this is the answer. Well, I'm sure they're going to give it to us if you put it all in your calculator at one time. This is, I think they say this is the approximation. So just put 8 in all those, then find the answer, multiply it by 50 in pi, and that's your approximation. Did they do? Yeah, they went, and that's the approximation. So I just wanted to show you that sometimes the F is complicated. Sometimes the force that you have is complicated. It's not going to be easy like those other problems when you see it in the homework. I don't know if I would put anything this complicated. You saw already what was on the test. I showed for this part, the show your work part of the test. So as far as showing your work, because I mean, it takes a lot to think about it. I mean, now that you've seen one, I think there's going to be one on the homework. You'll see that you have to first create this F, and you have to exchange the x squared because we're dealing with that y axis because the oil is dripping down the y axis. It's going down. So you had to change that x squared to something else. And so you use the formula for the circle, and wherever the circle is located on the grid determines the formula of the circle. Is that it? Yeah, that was, oh, wait, there was one, I do want to show one more thing on that I wanted to show that last slide because it gives you, it just tells an approximation. So let me figure out how to bring this slide up. Current slide, there we go. All right. So this is the same problem, but they're saying, hey, give us an estimate. We just did the work to empty a tank. They want you to estimate the reasonable, consider that, just look at the weight in the oil tank. And the tank is half full. The volume of a sphere is 4/3 pi r cubed. So I mean, that's hopefully something we know, or if we don't know, we look it up and take a look at it. 4/3 pi r cubed, that's the volume of the sphere. And the density or the weight per each foot, like they're saying, was 50. And then they just multiply all this together. And this is the answer, 53,000 pounds. And then they're lifting the entire tank of oil. 8 feet would involve this much work. And so if you looked at it down here, it says, because the oil is actually lifted between 8 and 16 feet, it seems reasonable that the work is done. You see, this is the end. The bottom is the answer we got. But they're emptying it out, and this is the work you would get just raising the ball up 8 feet to empty it out, but you're not actually emptying it out. So they just wanted to show you that, hey, it's reasonable. I mean, yes, it takes more work lifting it up and emptying it out than it does just lifting it up. Okay, let's go to the homework. And the homework, we're just going to do a couple of basic problems there. Okay, let's find, I should have put this at the top. All righty, I'm telling you. what is going on? Which ones did I want to do? Let me see if I marked any. Oh, 1, 2, 3, and 6. Determine the work done by a constant force. The locomotive freight train has 9 tons. The distance of a 1/4 mile. Now look, they want the answers in foot-pounds. Remember, determine the work done. Work equals the force times the distance. So 1/4 mile, we have to figure out how many feet that is. Anybody know? How many?
15?
Say that again.
5,260 feet in a mile, so divided by 4.
You're close. If you cheated, you would have looked at this. You said 60, right? It's 5,280. Okay, so it's 5,280 feet in 1 mile, and we're going to divide it by 1/4, so we get 1/4 of a mile. So whatever that.
It's 1320.
1320. Thank you. So we have 1320 here. And the force, 9 tons. 1 ton is 2,000 pounds. That's one of the good US measurements that actually is normal. I wish we'd stay in, we would have stayed in metric. Do you know we try to go metric, the US? Anybody know what year the US tried to go metric?
I remember hearing about it, but I don't remember when it was.
I think it was Jimmy Carter back in 1976. I mean, he actually got in the nation the speed limits, the speed signs on the highways that used to say 55 back then, or I think it was 55 back then, just have the miles per hour and kilometers per hour. We had both speed signs at the time, which is kind of weird. Because we really made a push to change metric, and when Jimmy Carter left, people just didn't catch on. You know, we can't even learn our own system. How are we going to know everybody else's in the world? It's everybody else in the world. Let's match up to them. So anyway, 9 times 2,000, 9 tons is 18,000. So we're just going to multiply those two together. And that's what you should get. So all we're doing is converting that to what we had to. A metric is so much simpler. And I always, especially when I teach my class temperatures, and in math 1332, I get a lot of culinary arts. And I ask them, at what temperature does water freeze? And most people know that. Anybody know what temperature water freezes in the US?
2 degrees.
32 Fahrenheit, 0
Yeah.
Celsius.
Yes, 32 Fahrenheit. And for everybody else, it's 0 degrees Celsius, yeah, in the world. Perfect, 0 degrees, you know, you got ice. Us, it's 32. Now, here's one that I love asking the culinary arts, because they should know this. At what temperature does water boil? All the culinary arts should know, right? You can boil
186?
water. Close.
Or 212?
212, yeah.
There we go.
200. And the metric, what's the metric equivalent?
100.
100 degrees Celsius. It freezes at 0 and boils at 100. How much easier can you get? It's such an easy system. Why wouldn't we use it?
I always like the response when it comes to metric or anything. It's like, well, it didn't get them to the moon. We got to.
Yeah.
We're the ones on the moon.
Yeah, we are so backwards. I don't know how that works. We are such a backwards country. I don't know how that worked. All right. Anyway, so here's once again spring, right? Spring problem. A force of 7 pounds compresses a 15-inch spring 3 inches. So, I mean, normally when you do these spring problems, try to just look at that first part, and we see if we, because they don't tell us the constant, compressing the string 7 inches more. They don't tell us the constant, so we have to find the constant. Force equals the constant times the distance, right? And it says here a force of 7 pounds, and we're moving at 3 inches. So divide by 3, K equals 7/3. So when we're in our formula, work equals force times distance. And the force is K times D. And K is 7/3 X dx. And it says how much work is done by compressing the spring 7 inches. So it doesn't say 7 additional inches. It says 7 inches. In other words, the spring is all the way expanded. It's not compressed anymore. It's all the way expanded. So we're going to compress it 7 inches. We're going to go from 0 to 7. So the previous problem says an additional, how much force is needed, or work is needed to stretch it an additional 3 inches. So we did it from 3 to 6. But here it just says you have this spring, how much work is to compress it 7 inches, not 7 additional inches. So we uncompressed it and we're starting from 0 again, and we're going to go to 7. So this is the formula. If I could write it down, there we go. So we just integrate 7/3 x squared, and then we bring the 2 down to the bottom. So this is 7/6 x squared, and we're going to go from 0 to 7. And so now when I grab my calculator, just put it in there. 7 times 49, 7 squared, and divided by 6. And I get 57.1. 0.1666666. It brings up a really good problem. If you type this in, what's going to happen? If you type this in, answer in right here, what's going to happen? It's going to mark it wrong because it doesn't say rounded or anything like that. They want you to type in the actual fraction. This is an approximation because it's a decimal equivalent. So you need to make sure you're typing in the fractional equivalent, which is right here. So I just wanted to make sure everybody understands that. And that's in inch pounds because we're stretching it. It said inches. And then they even converted it, I guess, to foot pounds force. And all they did was, it looks like all they did was divide it by 12. But they're not asking that. They just said in inch pounds. So everything was done in inches and pounds. So this is inch pounds. All righty. Okay, so this is the spring problem that's a little, has a little extra step to it. Not an extra step, but it's a little different. It says 4 1/2 foot-pounds of work is required. So they told us 4.5 foot-pounds of work is required to compress the spring 4 inches. From its natural position. Okay, so that's the beginning. We have to find K. But do you see our formula? Our formula was work equals the integration of force times dx. Work equals integration of kx dx. Now they gave us the work. The work was 4.5. They didn't, where is it at? 4 inches. Oh, by the way, this is really important. I should have mentioned this right away. Right away, you should know what your answer was going to be. And it's going to be in foot-pounds. Foot-pounds. So they said 4 inches. How many feet is 4 inches? 4 out of 12.
Third.
Yeah, it's 1/3. 1/3. So obviously, they actually integrate this right now. I mean, this is the formula. If you're going to integrate the x, so let's integrate the x. You get x squared over 2. Okay, x squared over 2. If we integrate the x, x squared over 2. Okay, and we integrated it from 0 to 4 inches, which is 1/3. Let's plug in 1/3. See what happens. That's 1/3, not 1/2. So we're going to plug 1/3 into here. So I get 1 divided by 3. I wish I had my other calculator. Raised to the square. And then 4.5. Oh, I'm going to multiply. I'm going to take this 2 to the other side really quick also. That changes that to 9. I mean, it's just all it is algebra. 9 equals k to the 1/9. 1/3 squared is 1/9. I think that's right. Something's not right. Something doesn't seem right. What did I do wrong? 1/3 squared is 1/9. Oh, we don't care about this. We're just looking. Yeah, no, we're fine. No, we're doing good. Good. Everything's fine here. If I bring the 1/9 over, I multiply by 1/9. I multiply by 1/9. I'm just not doing it exactly like they're doing it. If I multiply by 9 and I multiply. I get 9 equals k to the 1/9. And if I bring the 1/9 to the other side, I get 81. Multiply by 9, multiply by 9. K equals 81. That's the formula, K equals 81. So now we can actually, that was the first part, finding K. That's what I said. This one was a little bit different to find K. The other one we did was really easy. But this one, they give you, in the first statement, we have to find K, and they give you the work this time. So we integrate the blank, we just integrate this, and then we're solving, we plug in the X, and then we're finding the K. K ends up being 81. So then our formula is work equals integrating 81x dx. There's the K is 81x, and this is our integration. So it says now we can read the rest of it. I'm going to erase this. Now we can read the rest of it. I mean, that was all that work was just to find K. Now the rest says, find the work required to compress the spring an additional 1/2 inch. What? Is that right? Is that what it said? Find the work required to compress the spring an additional 1/2 inch. Then it says round your answer to 1 decimal place. So we started an additional. So we had the spring compressed at 1/3 at 4 inches, an additional 1/2 inch. So are we saying 3.5 over 12? Really wish I had this calculator because it does great with fractions. What happened to it? Oh, another one of those. So they're saying an additional one, okay, 1/2 inch then, you know, if 1 inch is 1 out of 12, 1/2 inch is 1 out of 24. Everybody agree? This is 1/2 inch. 0.5 over 12, 1/2 inch out of 12. So if I multiply the top by 2 and the bottom by 2, this is 24 of a foot, because we have to change everything to feet. So an additional 1/2 inch is 1/24. So I'm just going to show you how they got to the 3/8. It's 1/3 plus 1/24. Multiply by 8 and 8. You get 8 over 24 plus 1 over 24. So you get 9 over 24, which you divide both by 3, and you get, no, you can't. 24 divided by 3 is 8. There you go. That's how you got the 3/8. That's an additional 1/2 inch. It's kind of weird to see that. We had it compressed 1/3. An additional 1/2 inch is 1/24. So 1/3 plus 1/24 is 3/8. So there's a lot of fractional math. It's good to have a calculator that actually does that fractional math. Oh, and no, I should be using the TI-36 Pro. I haven't even turned it on yet. But anyway, there's our integration there on the right. So we have to integrate this from 1/3 to 3/8. 81x dx. So when we integrate that, you get 81x squared over 2. And you integrate it from 1/3 and 3/8. I would practice these fraction ones on your on your calculator to make sure your calculator does fractions well. The The TI-84 will also change it to fractions. You have to go math. So you have to hit the math button, number 1. We'll change it to a fraction, your decimal to a fraction. So when you do this, I'm not going to plug it in and do all this, but when you do this, you should get 1.2. Put 3/8 in there and then subtract, put 1/3 in there, and you should get that. All right, there was one more I wanted to do.